Hi, this is Sung. I'm your online maths mentor, and we've been going through applications of calculus to the physical world. In particular, we're looking at the extension 1 component. We've been doing things like motion, projectile motion, which looks at motion in two variables, both the horizontal and the vertical components. We've also looked at simple harmonic motion. What I want to do in this episode is look at rates of change. Now we basically know this about rates of change. When you see the word or phrase rate or rate of change, or the rate at which something is changing, usually we mean the derivative, right? The derivative of, or the rate at which something is changing with respect to time. It doesn't always have to be time, but usually we're talking about something changing with respect to time, okay? So basically, when you see in a question the rate at which y changes, what we're looking for, or what that should tell us, right, is that we're dealing with the derivative d of y dt with respect to time, all right? The change in y over the change in time, okay? All right, so what else can we know about this? Using the chain rule, or the function of a function rule, if you remember what that is, we know that the change in y over the change in time, another way you can express it, is the change in y over the change in x times the change in x over the change in t, right? Or the change in time. Because just by looking at how this works in terms of properties of a fraction, the dx here and the dx there, the one on the top and the one on the bottom, they can cancel out, leaving the dy dt, okay? So essentially, that is the chain rule. And we often use that when we're dealing with questions that deal with rate of change. And I've got an example up on the board that could be very useful for us to really demonstrate how the chain rule works. And this is really where the extension 1 component comes into it. So let's read this question and have a go. All right, let's have a look at this. A melting snowball, which is always spherical in shape, is decreasing in volume at a constant rate of 8 cubic centimeters per minute. Find the rate at which the radius is changing when the radius is 4 centimeters. Okay, so let's break this down. Let's break this down as much as we can. We've got a melting snowball, and it's spherical in shape. So that's my best attempt at a spherical snowball. Okay, hopefully you can see it's a sphere, and it has a specific radius. Okay. The relationship between the volume and the radius for a sphere is that the volume, hopefully you can read that, is 4 on 3 pi r cubed. Now that's the volume, okay, expressed as a relationship of its radius, okay? All right, so that's what we know. Let's look at the next bit, okay? We're told that it's decreasing in volume at a constant rate, right? So what's rate mean? Rate means derivative of 8 centimeters or 8 cubic centimeters per minute. So we're told that the rate of change of volume with respect to time, okay, is going to be a constant rate of 8 cubic centimeters per minute. Okay, does that make sense? All right, and then it says find the rate at which the radius is changing, right? So we want the rate at which the radius is changing, which is the dr dt. So when we see the word rate, right, we're looking at the change in the radius with respect to time equals to what when r equals to 4. Do you get that? Cool. All right, so we need something intermediary. Like, what is the connection between that and that? Well, let's do it this way. The change in volume with respect to time is equal to the change in volume with respect to the radius times the change in radius with respect to time. Got it? So we're going to use that property. Now, where do we get that property from? All right. Essentially, we get it from the chain rule, which is this one here. Okay. So we know what this is. We know that that's 8, right? We need to find what this is, right? And in order to do that, we need to find what that is. Now, how do we find the change in the volume with respect to time? Well, we use this relationship here, all right? We know that the volume is 3/4 pi r cubed, so we should know that the derivative of that with respect to radius is going to be the derivative of that. So you multiply by the power, take 1 off the top, so it's 4 pi r squared. Got it? Okay, so let's fill that in. So that's our key. All right, so let's look. So that's going to be equal to 8. That's going to be equal to that, which is 8. Whoops, not 8. 4 pi r squared. And that's what we've got to find, right? We've got to find that. Times dr dt. So dr dt is actually going to be equal to 8 over 4 pi r squared. But the only thing that's stopping us from finding that is we don't know what r is, okay? And we're told that r is equal to 4. So I'll go one more line. The rate of change of the radius with respect to time is going to be equal to 8 over 4 pi r squared. Got it? Cool. Which should end up giving us, and I'll do this over here. Okay, 4 squared is 16, times 4 is 64, 8 goes in 64 8 times, so it's 1 on 8 pi, and it's going to be in centimeters per minute. Because remember, this was in cubic centimeters per minute, and that's the rate of change of the volume with respect to time. So the rate of change of the radius would be centimeters per minute. Got it? All right, so that should be the answer. Let me just work that out on my calculator so that we can come up with some numerical value. All right, so hold on a second. So I get that the rate of change of the radius with respect to time is 0.0398 centimeters per minute to 3 sig figs. All right, does that make sense? Have a look at that particular question, go through it, see if you can understand the principles of how we apply the chain rule to rate of change type questions. And if you can understand that, you'll pretty much understand how to do the bulk of the extension 1 rate of change questions. Thank you very much for watching. Bye.